Hello everybody, my name is Chris, I'm a TA for Data 100. This is discussion 11 walkthrough for questions 3 and 4. To start off with, let's go ahead and do question 3A. Go ahead and take a minute to read the question to yourself, pause the video, do the question, and come back when you're ready to move on. So, your friend has argued that we can linearly the data we have here are linearly separable because we can put a line through them, which is in fact true when you draw them on a 2D coordinate system. But what's important to note is that we can only separate these lines because we can draw this linearly separable line between the two classes that we're predicting. As a matter of fact, because we're only going to be predicting on this one-dimensional feature x, it's not as simple as it would look. Take a moment to note that no matter where, if I draw a vertical line through this plot, there's no point at which I'm drawing this line where I'm separating all of the red dots on one side from all of the blue dots on the other. And this is an important thing because linear separability is only relevant in the feature space. If we include the output space, then we've lost all semblance of meaning when we're talking about linear separability. Of course, classification points are going to be linearly separable if you include the output space because they're discrete values. We can always draw a line between those discrete values based on the fact that we're doing a classification problem. So your friend's argument is incorrect because it includes a portion of the space of our data points that is not relevant to the problem of linear separability. A more salient plot to use would be this kind of a plot, this rug plot we have here, where we can see the x values for each point and then color-coded. And we notice that no matter where we draw, again, this vertical line, we're never going to separate the blues from the reds, right? We can see, you can take these two, right? We have a blue on the left here, but a red on the right, and a bunch more reds over here. We're never going to be able to linearly separate these, and thus the data is not linearly separable. It's an important point about linear separability that it's only relevant when we're considering the feature space of our data, not the outcome space. Now let's move on to question B, part B. Go ahead and take a minute to read the question to yourself and do it, and come back to the video when you're ready to move on. So suppose you train a gradient descent on a logistic function model on two design matrices XA and XB and use some stopping criterion. The stopping criterion they're describing here is that the maximum absolute values of the components of the calculated gradient is smaller than some threshold t. Basically, this is saying that the gradient is going to be so small that its maximum component is smaller than some value provided t. But this basically means is that the gradient is small enough that it's the direction of the change is negligible, and we've basically arrived at a local minimum. After training, you find that the training accuracy for XA is 100%, and the training accuracy for XB is 98%. So let's think about XA first. So we know that our training accuracy is 100%, which means that we've built a classifier that can classify every point in our data set. Now, a key thing to note is that in the feature space, this is only possible if we have linearly separable data. So because our training accuracy is 100%, we know that it was possible for this classifier, given, for example, let me draw some data. So it was possible for our classifier, let's say that XA contained these points and these points. Our classifier was able to find some optimal boundary, like this one, that linearly separated the data. So it's important to know that if you achieve training accuracy of 100%, that is only possible because data are linearly separable in a feature space. But now let's think about XB. We've only been able to achieve training accuracy of 98%. So after quick inspection, one would think that that indicates, well, if we can't do it, if we only got 98%, that means that we can't linearly separate the data, right? But that's not necessarily the case. Remember that gradient descent is a numerical analysis algorithm, and that doesn't always find the perfect solution. In fact, if your loss function is not convex, it's very easy to get trapped in bad local minima. So it's certainly possible that the algorithm that is being used for training on XB just didn't find the optimal boundary and got stuck at some bad local minimum here in this loss function, if it looks like this. So while we can't say that XB is definitely linearly separable, we also can't say that it's not linearly separable. So XB, maybe. We don't know. We can't tell based on this information because we don't know that we haven't seen the data. All we know is that it got a training accuracy of 98%, and we don't know how that data was trained. So as of now, we can draw no conclusions about the linear separability of that matrix. All right, let's move on to question 4a. Please take a moment right now to read the question and do it on your own. Pause this video and come back when you're ready to move on. So let's start by drawing out our 2 points in this question on a 2D coordinate plane. So we've got 2 axes, x1 and x2. Our first point, which is in y equals 0, lies at 1, 1. So I'm going to do this there, and I'm going to color that point red. Our second point, which is in the other class, y equals 1, is at 1, negative 1. So I'm going to put this one here in blue. So we see that our two classes, which are defined by the colors red and blue, have a bunch of space between them, and they are in fact linearly separable, which we can tell visually just by looking at them. So I'm going to go ahead and draw just a random hyperplane through them, and I'm just going to choose the hyperplane x1 equals 0. So, as in summary, yes, they are linearly separable. We can draw a line through them. And let's move on to part D. Go ahead and take a moment, read the question, do it on your own, come back to the video when you're ready to move on. Okay, recall that from part A, our points are linearly separable. This implies that we can achieve a cross-entropy loss of 0. That's possible for us because we can draw a decision boundary that correctly classifies every point. But remember that our sigmoid function, sigma t, is only defined on the open interval 0, 1, which means that we can never actually get sigma of t to be 0 or 1 for any t. This is the problem though, because we are always going to be trying to continually minimize our cross-entropy loss to get it to go to 0, which is possible. But we can never actually achieve cross-entropy loss of 0 because of the sigmoid function that is not defined at the value 0. So what this means is that our cross-entropy loss will always try to get closer and closer to 0. But this is never going to be possible because remember, our sigmoid function can never be equal to 0. So as this time keeps going on and our gradient descent algorithm brings us arbitrarily close to 0, we're going to end up with weights beta that approach infinity as time goes on because there's always going to be a bigger beta hat that gives us a smaller output of sigma or a larger output and makes cross-entropy loss go smaller. For this reason, we can never actually minimize cross-entropy loss because there's always going to be a bigger beta. One thing we could do to prevent this from happening is by regularizing our loss function. So we end up with cross-entropy loss, L of theta, given x and y, is equal to the sum from I equals 1 to n of yi times log of sigma phi of xi transpose theta plus 1 minus yi times the log of 1 minus sigma phi of x transpose theta plus the sum from I equals 1 to d, because we have an n by d feature matrix, of lambda times the weight theta I squared. This will prevent us from winding up in a situation where we can never actually minimize cross-entropy loss. All right, that's all I have for you. Let's go ahead and continue on with the next question about multi-collinearity. And please put some comments if you have any questions.